Okay.
I forgot to do the assignment for US.
Are you guys ready for this final that's coming up?
Maybe.
No.
It's gonna be multiple
If I
choice.
bombed one of those tests.
It's going to be just like a regular test.
Then I'm probably.
Wait, how,
okay.
can we get a review for this?
Yeah.
Wait.
The only child.
Are you ever here in the room, Emily? Goodness.
She's in the room. She's not
Second hour, right
She's
after.
in the room.
All right, for
She's
government,
not
what does that
in
mean?
the room.
Government's a good class, this is a crappy
I
class?
just
Earth,
like-
Earth family. We're in elementary. They tell us like,
Oh.
oh, no
Oh,
stuff
yeah.
in space
I feel like
will
that's the class
crash
you
you
should
down.
focus, right? Isn't that a
That's
subject
stupid
class or is that a
teacher.
Mr. Fisher
I'm
class?
in second grade. I don't need you. Forward to funds.
What? Although you actually were one of the probably few that really enjoyed singing.
Except I don't. I
Be
tried
careful
all
what I
the
said,
pitches.
because
That's more fair to say. I
All right, today, not an overly complicated lesson. Did you guys read up on surface tension and capillary action and the difference between cohesion and adhesion and viscosity? Because I asked you to do that. Did you do that?
No, I didn't do it at all.
You remember that from last year? So what's the difference between cohesion and adhesion?
Cohesion's like the thing like in the tube with the tube.
Cohesion's to itself. Adhesion's to other things.
So it's, I was thinking the other way around.
Yeah, cohesive. Think of adhesive tape.
Yeah, or glue.
Like adhesive tape would be like sticking tape to something else, right? So it would be something attracted to something else. Does that make sense?
Cohesion,
Okay. Yeah, cohesion is
Like oil on
so both of these are intermolecular force attractions. Does that make sense? Cohesion would be like the intermolecular forces in water attracting
Only water.
water.
Yeah,
Another water molecule. So that would be your traditional intermolecular force attraction.
So it would be like the water forming a B on a windshield. So instead of spreading out.
Okay, so that would be a cohesive effect. Adhesion would be like water being attracted to a paper towel.
Yeah.
Okay, there's intermolecular forces in a paper towel, and if water's intermolecular forces are also attracted to the paper towel's intermolecular forces, you get that force of attraction. That's called adhesive. An adhesive attraction or an adhesive force. Okay. So I don't know if you guys remember capillary action. So capillary action is an adhesive effect. As it says, the spontaneous rising of a liquid in a narrow tube. We talked about this is how plants get water from their roots up to their leaves. Their stems are actually really small, and so the water is attracted to the stem, and so it rises up due to that attraction. Now it needs to be a relatively small orifice.
Hole? That's what
Yeah.
orifice.
Yeah. Look at that. See, I know
Word
how
of the
English
day,
is.
orifice.
I'm improving in my English skills.
Great
I'm hanging
word.
around you guys a little bit.
Use the word orifice every hour if possible. It's amazing.
Who?
Everyone should use the word orifice.
She's just
whenever
not in the
possible.
room.
It's an amazing, not awkward at all. Orifice.
Okay, last thing I do want to talk about of those things I wanted you to read, I am going to spend a few, but just really a minute on viscosity. Okay, definition of viscosity is what?
Thickness, resistant to flow.
Opposite of that, the ability to resist flow. Okay, so if you have something that's very viscous, it flows well?
No.
No.
Maple syrup.
Okay, so it doesn't flow well. And believe it or not, viscosity is an intermolecular force thing. Okay, if something is really attracted to itself or has a lot of cohesion, yeah, we call it narcissistic, and it doesn't flow well. It just wants itself. It's just sit in its little ball of fluid and just hang out by itself. Same.
I have an idea. For our study, we should bring in, like,
I want to be.
Yeah.
My notes are so funny to me when I'm exhausted.
That sounds
Not everyone else, but
With not just regular pancakes.
No, but like I've had.
Oh, okay. Well, your test is on Monday, so we can do it Sunday night.
because I overthink them. Got tired of
Yes.
them.
So high viscosity means high or low intermolecular forces. Okay. Alright, let's get to today's stuff. There's a good amount of today's stuff. Oops, we talked about that. Okay. Good amount of today's stuff that is review. All of these vocab words are not new vocab words. But new this year. The top two are new this year. We talked about crystal lattice, didn't we?
Vaguely.
Okay. So you should remember that there are two types of solids. There's crystalline and amorphous, and they're pretty easy to distinguish the difference between the two just by their names. A crystal is something that you would think of as being very what?
Oh, we did have what this, yeah.
What did you say?
Or,
That's true.
Uniform.
Uniform, symmetrical, ordered, yeah, all of those things. Okay? So a crystalline solid is one that has a regular arrangement or very repeatable pattern, and amorphous is one that does not.
Like all wax.
Yeah.
So different.
Yep.
On
Okay? And here's kind of the thing that you might want to make sure you know about this. Crystalline solids have all similar bond lengths and energy. And for amorphous, you have, I don't know how to word this, varying, yeah. Varying, is that how it's called? Varying? Okay. Varying bond lengths and energy. Okay? So, what is this going to do to some properties? You think this is going to have an effect on properties?
Yeah.
Okay, so we talked last year about how this affects boiling point, or melting points. And it would affect boiling points too, but it's easier to think of it from a melting point standpoint. Do you remember how this affects melting point from last year, Riley?
Crystalline solids, because it's a uniform structure, all the intermolecular bonds, in quotes, all break at the same exact time. Amorphous solids, it melts gradually and softens and gets gooey.
Yep. Yep. I mean, I don't think I could really explain that any better. Because these have similar bond lengths and bond energies, they all break at the same temperature.
You give that future classes.
Yeah, pretty much. Okay, they all break at the same time, same temperature. Okay, but if I have different bond lengths and bond strengths and bond energies, then the weaker bonds will break at a lower temperature and the stronger bonds will break at a higher temperature. And so what you have is melting points that happen over a temperature range. Now it's not a huge temperature range, but it could be anywhere from a 1 to 5 degree temperature range. Versus this is all happening at the same temperature. Okay? This is coming back to us a little bit here.
That's cool to think about it though.
Yeah, I've seen this under a little melting apparatus thing. You kind of look in, you can see it's slowly melting.
Yeah.
So is water,
Water is very much crystalline.
Yeah. It all melts at the same temperature. It might be at the same time.
So an example of amorphous, the best example I can give you is wax. Okay? And the reason why you get amorphous solids, there's typically things that freeze or solidify fast. They don't have the time to arrange their bonds in a way that's ordered.
Oh, so if you cooled melted wax slowly, would it make crystal?
In theory, I've never done it or heard of it being done, so I wouldn't know the complete answer to that. Okay? And your crystal lattice there, your lattice is your three-dimensional shape of these solids. Okay, this is probably specifically your crystalline solid, but you can think of your crystal lattice as the solid structure would be your crystal lattice. Okay, and then if we're talking about a crystal solid, then if we have a very repeatable pattern, your big overall structure can be broken down into smaller units, which would be called unit cells. And again, this is review, nothing overly crazy. There's something I wanted to turn to. Let's make sure that I still want to turn there. Yeah, why not? Turn to 445, 446. So just giving you, again, I'm not going to make you memorize this stuff, but at the bottom of 445, you have a couple crystals, a couple solids there. What type of solids do you think that is? Just by looking at it.
Yeah.
All these two solid types. Carbon? Yeah, crystalline, right? Very structured, orderly shape. If you flip the page, you can kind of see the difference between your unit cell and your lattice, or your crystal lattice. Your crystal lattice is the big structure, okay? And your unit cell is the repeatable pattern that you would get to get your big structure. Does that make sense?
Change the direction of the first lattice picture.
Okay? And those little spherical objects there that make up the shapes, those are what are called your lattice points. A lattice point is specifically where you would find your either atom or your ion or your molecule. You could have different things at those lattice points. For example, if we're talking about H2O crystalline solid, what would be at your lattice points? If we're talking about water as a solid, what would be at your lattice point?
The two hydrogens at one end and then the oxygen together.
No, you're not going to split up the water molecule. Your lattice point is your water.
Oh.
You got H2O at one lattice point, and then you got a different H2O at a different lattice point attracted by those oppositely charged polarity. Okay? If I'm talking about an ionic compound, what's at your lattice points? This is an hard question. Ions. Okay? Alright, so I think the next group of things here are types of crystalline solids. So I don't know if that's actually in your notes. So you might want to write, does it say? So whenever you start saying ionic solid, you could write that section, anywhere from ionic solid below, is going to be types of crystalline solids. Right here I said?
Yeah. Anything below it?
Yep, so I think you should have ionic, you should have molecular, atomic, metallic, and like noble gas or something like that.
Ionic solid?
So there should be 5. Well, 3 main types, and then there's okay, so yeah.
Say below
Like everything from ionic solids to the rest of the lesson. So you have 3 types really, and then you've got one that has multiple. So your first type is an ionic crystal. Second is going to be a molecular. And third is going to be atomic. And then you have 3 types of atomic crystals. Should have made that the middle one. One is metallic, is that correct? Another is noble gas. Network covalent too?
It says network solids.
Okay, so network solids or network covalent. And then, what did I say last one? No gas?
No gas.
Okay, so you're going to want to put a star by this. This is one of those things that just gets forgotten when the test comes around. Okay? Now, what these are, again, we're talking about crystal solids, so they're going to have very repeatable, ordered structures, correct? Okay, so they're going to have a crystal lattice shape, and they're going to have a unit cell, correct? Okay, and in their unit cells, they have those lattice points. Okay, and this is where you've got your differences in your lattice points. Okay, what's going to be at the lattice point of an ionic solid? Ions. What's going to be at the lattice point of a molecular solid?
Molecules.
What's going to be at the lattice point of an atomic solid? Atoms. Now there are 3 types of atoms they break this down into. Metallically bonded things that are going to have atoms at your lattice points. Network covalent, that's like diamond if you want to write that as an example. What makes up diamond?
Carbon.
Carbon. So you have carbon at your lattice points, making a nice 3-dimensional strong structure known as a network covalent or diamond. And what do you think is going to be at the lattice points of your atomic or your noble gas type? Noble gases. Okay. I can't ask simple questions in this class. I can't.
That's your question. All right.
Okay, so that's kind of what all these things are saying. Okay, your ionic solid is going to be, you've got your anions and your cations that make up your lattice points. Okay? Molecular solids are going to be, you're going to have molecules at your lattice points. This could be any molecule that has polarity. Well, any molecule period, because you could take anything that has nonpolar and still make it a solid too. Okay, so like water, H2O could be at the lattice points, or carbon dioxide could be at the lattice points, or methane could be at the lattice points. You can keep going on and on and on. What's specific about molecular?
They're large. Never mind.
It has to be covalent.
That's never.
By definition, molecule is a covalently bonded thing. Okay? So this would be specifically covalent. This would be specifically ionic. I know they didn't say ionic, covalent, atomic. They said molecular, but you'd have to remember that a molecule is the covalently bonded type. Okay? And then you've got metallic. So you've got your 3 main bonding types: ionic, covalent, metallic. And these guys are your I don't know, I guess you could call it your exceptions or goofier ones. Right? Let's see, what else? Okay, closest packing. Let's see, turn to 451. There's a pretty interesting, on 450, some crystal lattice structures of your diamond, your sodium chlorine, and your water molecules. See the repeatable pattern in all of those? Diamond actually looks like the least repeatable pattern, but that's because it's just a smaller structure. Okay? So on 451, you've got your closest packing is what it's called. I'm not going to make you know too much about this. All this simply is the most efficient way to pack metallically bonded substances. And you can kind of see it's a shape made up of seven objects. And you see how if you take that that shape and you twist it a little bit, you turn it and you move it, you would get this nicely packed crystal lattice structure. Now, I'm not going to talk too much about that. But if I am talking about ionic compounds, what's the theory that maintains that these are, not ionic, sorry. If I'm talking about metallic, what's the theory that holds metallically bonded things together? Electron C theory. Okay, the electron C theory. Okay, so what you have is those things packed in this closest packing, or HCP is another way it could be done, hexagonal or cubic, depending upon what metallic structure is being bonded. Those are being held together by the free-flowing electrons. last thing I think we needed to talk about is an alloy. Is that in your notes? Do you have alloy in your notes?
Yeah.
Two different types of alloys, is that true? Okay. Good, we're perfect on time. Okay, you guys all know what an alloy is, right? Alright, what is it? Mixture of metals, give me some examples.
Steel.
Steel, okay?
Bronze.
Bronze, yep.
Um,
Instruments are made of brass, okay? Alright, so you got two types. You got substitutional alloys, okay? This is where you've got some host metal that gets replaced by some other metal of similar size. So an example would be brass. Brass is 1/3 of the atoms of your host copper have been replaced with zinc. So essentially you take 1/3 of the copper out and you infuse zinc in its spot. Still a mixture, right? Okay? Gives it a little bit different structure, a little different strength. There's a couple other examples. Sterling silver is an alloy, substitutional alloy. Pewter or plumber's soldier. I don't even know what that is, but it's an example.
So
You might know.
they're not as strong.
Usually, yeah. No, yep, they're not going to be as strong. Because you're replacing versus. So let me finish by saying your I can never say this word. You guys probably say it. Yeah, stitial. Yeah, sounds right. But this is like, do you guys remember me talking vaguely about shot peening last
Yes, I
year?
do.
Yeah, okay. So this is what shot peening is. It's when you take metal and you actually like infuse or shoot more metal into the little gaps.
You shoot
in
balls
this-
at it so it smushes it together.
Yeah, so well, I don't know if smushes, it's quite the word. Well, do you guys remember what property of metals allows this to happen?
Malleability.
Malleability, right? Because it's malleable,
This chapter.
you can shoot what?
I remember this.
Yeah, you got this stuff down.
Can you read that sentence?
What sentence?
Yeah, it's not